Hello everyone, welcome back to the air learning modules for Underhood thermal application, using SimLab as the preprocessor and AcuSolve as the solver. This is the fourth and final video. I will set up the flow domain, the heat exchangers, and the moving reference frame. After running the solver, I will post-process the result from AcuSolve. Let's revisit the problem description. The flow field is driven by the fan rotating at 1500 RPM. The large heat exchangers in the front and the smaller heat exchangers in the back of the canopy are there to cool the engine. Heat is transferred from the coolant into the air, increasing the ambient temperature inside the canopy. The engine will have thermal battery conditions applied on the exhaust manifold, the fin on the top, and the engine block. Notably, we will also model the air intake and the exhaust of the engine. Picking up from the last volume meshing video, in this video I will show you how to set up the flow condition for this problem. We go into solution, flow, make sure heat transfer is enabled. First of all, we need to set up the inlet for the domain. Flow gonna be going in positive Y direction. So the domain, the inlet domain gonna be this phase. I'll set it at 0.1 meters per second with a temperature at ambient 293 Kelvin. I'm sure it's auto. Okay, I will set the outlet for the domain too. Please make sure to have backflow condition enabled, with area average for temperature and the same for eddy viscosity. Click OK. And the four lateral faces gonna be slip. We need to hide the domain. And we need to set surface output for all faces of the blade so that we can get the torque. Click OK. So because the flow gonna go into positive Y direction, we also need to set surface output for the heat exchangers. So each heat exchanger is gonna have two surface output. So this in and this out. Large XX in, large HX out. Large 3 small HX in, small HX out. Okay. Now we need to set the exhaust. So the exhaust is exiting out of the engine. but for the flow domain, it's actually an inlet. So we're gonna set inlet for the exhaust. You can select the phase, or you can simply select the phase group that we have created earlier in video number 2. I'll call this exhaust 1. Either select this, or I can just select the phase group. I will change this into mass flow rate. It's going to exit out at 1 kilogram per second at 500 degree Kelvin. Click apply. And let's go to the other one, or you can just simply set it applied. I'll call this exhaust 2. And it's going to be exhaust tip number 2. The same mass flux of 1 kilogram per second, and the temperature is 500 degree Kelvin. For the engine air intake, it is an inlet for the engine, but it's actually the outlet for the flow domain. So I will set this as outlet. You can select the phase manually, or you can just simply set it applied with the phase group that we created. Make sure backflow condition is enabled. Click apply. What's special about the air intake is that we have to use advanced battery condition to set the mass flow rate of the outlet. We can go into advanced. Under advanced battery condition, we'll set surface integrated. And we set this as air intake mass flux. And we can either select this phase, or we can simply click on the phase group. So it will take in 1 kilogram per second. Click OK. So this is advanced battery condition to set a prescribed mass flow rate exiting out of the flow domain. I'll set the engine block also as constant temperature. Instead of selecting all of the phases, I will select a group. And we'll select 2 group. Let's put this at 500 degree Kelvin. So for the engine fin, so instead of selecting hundreds of individual small phases here, I will set it in wall, and I will just simply choose the phase group that I created. Call this engine fin. Depending on what you want to do with the battery condition, you can put it as constant temperature or apply flux or convection. For the simplicity of this demonstration, I'll set it as constant temperature of 400 degree Kelvin. I will also set a constant temperature of 2 manifolds. I'll select exhaust number 1 and exhaust number 2 because I am assuming that they will have the same temperature. If they have different temperature, of course I have to set them individually. 500. Okay, now I need to model the moving reference frame. Let's hide the domain. Click on the reference frame. I'll rename this accordingly. Click on the MRF region. And set the angular velocity of 157.08. And we can click on define axis as the cylindrical face. And make sure that it's rotating in the negative y direction using the right hand rule. Okay. Lastly, going to be our 2 heat exchangers. So in components, there is heat exchangers component built in SimLab. I'll set the large heat exchangers first. And the inlet face, because the flow is going in positive y direction, I'll select this face. Set the constant heat reject of 64,000 watt with the coolant flow rate of 0.1 meter cube per second. And the thickness, let's get our measure tool. It's going to be 0.15 meters. We can leave the upstream distance as 0 and the effectiveness as constant. The default is 1, but please make sure to set it as 0.95. The pressure drop, the default is constant, but please set it at piecewise linear. So in this table, we have to input the axial velocity and its corresponding friction factor. I will put the friction factor table on the screen, and you can take your time to type it in. Click enter to insert a new row. When you're done putting in the table, we can simply click OK. And this is our friction factor and versus velocity plot. The traverse friction factor we will put as 50. But these parameters is totally dependent upon what you have. And we're going to do the same for the small heat exchangers. The coolant heat reject for the small heat exchangers, I will set it as the 10,000 watt. With the same coolant flow rate of 0.1 meters cube per second. And the thickness is 0.15 meters. The effectiveness is also 0.95. Because of the simplicity purposes of this demonstration, I will use the same table with the large heat exchangers. But if you need to create a new one, you can do that too. The transverse friction factor, I will leave it at 50. Let's check the thickness, just to be sure. Okay, the thickness is 0.1 meters. We can edit that. This is 0.1. Okay, there we go. At this point, let's save the database. And rename our problem. Before we solve, please make sure to assign materials into these bodies. You can do that by going to Material, Built-in Database. And we use air with the default properties. It's already here. Windows select and apply air. Can right click onto the solution and export solver input files. Choose our working folder. Save. The export is complete. Now let's click OK. And we need to go into our working directory. Click to edit the INP file. Okay. We can keep everything as default. Need to put this at 0, 0, rotating in the negative y direction. That is correct. What we care the most about the INP file is we scroll down all the way to the heat exchangers component. And look at the heat exchangers definition. This is 0. Flow is in the positive y direction. And if we hide this domain, we also need to make sure that flow is entering through the positive y direction. But in the INP file, it's currently as a negative. So we have to manually switch that into positive. Okay, save. And let's turn on the AcuSolve command prompt. We're gonna cd into our working directory. We can acu run to start the solver, and we can specify number of processors. In my case, I have 28 with 20 physical cores, so I will request 20 physical cores. In the problem directory, we have acusim.cnf file already with the problem name specified, so we don't need to output problems here again. But if you don't have the .dnf file, you do need it. I can click OK to start the run. When AcuSolve has finished solving, we can right-click onto our solution and click Attach Results. In the working directory, we want to look for the log file or the extrude file. Attach result options, we can keep it as default. And let's choose flow post-processing because it is lighter on the graphic. Let's go back to our solution browsers. Right-click on the result and plot convergence to open AcuProbe. In AcuProbe, we can plot the final residual ratio to see how close we are to the Navier-Stokes equation. We can see that the velocity, the pressure, and the additive viscosity is quite converged already, but the temperature is not there yet. But it is okay. As long as it's not over 0.01, it is fine. Let's plot the solution ratio. Again, it is not quite converged to 0.01 yet, but it is very close. It is because the flow is inherently transient and not steady state. Now let's go to our two heat exchangers. And what we're interested in is the temperature at the inlet and outlet of each heat exchangers. We can see that there is a lot of surface output. So one belongs to the large heat exchangers for this example, and one belongs to the domain. It is because that the two axial faces of the heat exchangers are shared between the heat exchangers themselves and the domain. So when we place a surface output, it creates one belongs to the heat exchangers and one belongs to the domain. You can choose to plot whichever and they should have the same value. Let's go into temperature. So the inlet of the large heat exchangers is about 303, and at the outlet it is a little bit higher at 307. So there's about 4 degrees Kelvin or Celsius difference. This is because of the heat being dumped into the air at the heat exchangers. We can go into the small heat exchangers. Let's look at the inlet. The inlet temperature is gonna have about 349 or 350. And let's look at the outlet. So the outlet temperature is going to be about 356, so it's about 6 degrees Kelvin or Celsius difference. It is because of the heat being dumped from the heat exchangers to the air. Okay, let's exit out. Let's create a cutting plane right in the middle of the flow domain. Let's put it in the X normal direction. So the maximum temperature is going to be about 415 on this cutting plane. Instead of displaying contour, I can disable it and then display the vector to visualize the velocity field. Let's change the vector scaling from magnitude to uniform and make the vectors a little bit larger. Okay, so we have flow from the outside going in the canopy and going through the heat exchangers where heat is being dumped from the heat exchangers to the fluid. And this is our engine intake. You can see that the flows going into the engine intake. You can also see the temperature increase across the smaller heat exchangers. Now let's disable this and we can create a cutting plane right at the exhaust tip. So it's gonna be in the Z normal direction. So this is one of the exhaust tip. Now let's display vector. So the temperature at the exhaust is exiting out at 500 Kelvin. We can move it a little bit further so that we can take a look at the other exhaust tip right here. Let's disable so that we can go easier on the graphic. So the temperature is about 500 right here at the exhaust tip. And the velocity field should also be the same. Flow is going out the exhaust tip at 1 kilogram per second and collide with the wall. The last parameters of interest is going to be the torque acting on the blade surfaces. We cannot get the torque through AcuProbe because it is currently calculating with respect to the origin. However, if we take a look into the INP file again, we can clearly see that the rotation center of the reference frame is not at the origin 0, 0, 0. It has something else different. Now we need to get our AcuSolve command prompt and put in the AcuTrans command. It's gonna be AcuTrans OSIV, which is the variable, and we're gonna choose moment. OSIS is gonna be the surfaces we want to get. It's gonna be blade surfaces, or depending on what you have in the INP file, you can search the surface output. is going to be right here. The moment center, we're going to grab the one in the INP file. Scroll all the way to the top. We're going to translate it from the origin 0, 0, 0 to this center right here. Make sure there's no spacing between each comma. And if you click OK, it should appear this message. And going back into the working directory, an OSI file should be written. If you open it, and the torque at the steady state time step is going to be written at the very bottom. And because we are rotating in the Y axis, we don't really care about the X and Z moment. We only care about the Y moment right here. And it is going to be about 180.6 newtons meter. And that concluded the e-learning modules for the Underhood thermal application. Thank you for the attention. I hope you find this series helpful. We are here to support in case you have additional questions.